21 ECE 212T Control Systems Theory and Applications Unit 3 Part 1 Stability Analysis Poles and zeros of a system. Poles are the points where the denominator of g of s, that is the transfer function, is 0. They determine the system stability and natural response. Zeros are the points where the numerator of g of s is 0. They influences how the system responds to inputs or transient behavior of the system. If transfer function g of s equal to n of s by d of s, then poles are the roots of d of s and zeros are the roots of n of s. Concept of stability. The S-plane is a graph with two axes. The horizontal axis shows the real part of S-plane and the vertical axis shows the imaginary part. If all the system's poles are in the left half of this plane, the system is stable. If any pole is in the right half, the system is unstable. If poles lie exactly on the imaginary axis, the system is marginally stable, meaning it neither grows nor decays, but oscillates continuously. Introduction to Routh Hurwitz techniques. The system stability can be determined using different techniques. So one of the technique is Routh Hurwitz techniques. Routh Hurwitz techniques helps us find out if the system is stable without actually calculating the poles, which can be complicated for higher order systems. First, we write down the characteristic equation of the system. Then we arrange the coefficients into the first two rows of what's called Routh array. From there, we fill out the rest of the array using a simple formula involving determinants. The key idea is to look at the first column of this array. If all the signs are the same, the system is stable. If there are any sign changes, it means the system is unstable. This technique saves a lot of time and effort while giving us a clear picture of stability. Routh Hurwitz. Sometimes while building the Routh array, we face special situations. One of the situations is 0 in the first column. If 0 appears in the first column, we replace it with a very small positive number called epsilon and continue calculating. This helps us avoid division problems and still check stability. Next special case is entire rows of 0. This means the system has purely imaginary roots, which usually means oscillations. To handle this, we create an auxiliary equation from the row above the whole 0 row and use it to find these roots and understand stability better. Next, we are going to look into a numerical problem on Routh Hurwitz criterion. This problem involves the special case of first element of one row is 0. So the problem is analyze the stability of a system with the characteristic equation V of s equal to s raised to 4 plus 2s cube plus 3s square plus 6s plus 5 equal to 0. So to construct the Routh array or to analyze the stability using Routh array, the first step is to construct the Routh array. The first two rows of the Routh array are formed directly from the coefficient of the polynomial. So our characteristic equation is given as s raised to 4 plus 2s cube plus 3s square plus 6s plus 5. So row 1, we take the coefficient of s raised to 4, s raised to 2, s raised to 0. The coefficients are 1, 3 and 5. For row 2, the coefficients of s cube, s raised to 1 are taken. So the coefficient are 2 and 6, and we add 0 for the remaining space. So the initial Routh array is s raised to 4 135, s cube 260. To calculate the subsequent rows, the elements of a square row are computed using Aij equal to determinant of 2 by 2 submatrix divided by elements in the first column of the row above. So to find out the first element of a square row, element is equal to determinant of 1, 3, 2, 6 divided by 2. So this will be equal to 6 minus 6 divided by 2, that is equal to 0. The second element of a square row is element x equal to determinant of 1520 divided by 2. So that will be equal to minus 5. So the square row becomes 0, minus 5 and 0. So here we are getting a 0 in the first as the first element of a row. So when 0 appears in the first column, replace it with a small positive number epsilon and proceed. Let's assume epsilon is greater than 0. So the updated array is s raised to 4 135, s cube 260, s square epsilon minus 5 0. Now we can continue calculating the s raised to 1 and s raised to 0 rows. So we can calculate the s raised to 1 row first element as determinant of epsilon minus 5, 2, 6 divided by epsilon. So that will be equal to 6 plus 10 by epsilon. And for the second element, we can calculate it as epsilon 0, 2, 0 divided by epsilon. So that will be equal to 0. So the s raised to 1 row is 6 plus 10 by epsilon 0. The next row, that is s raised to 0, can be found out as 5. So the complete Routh array is for s raised to 4 row 135, s cube 260, s square epsilon minus 5 0, s raised to 1 6 plus 10 by epsilon 0, and s raised to 0 is 5. So now let's substitute epsilon equal to 0, or let's consider epsilon is a smaller positive number. So we can see if we substitute epsilon equal to 0 or epsilon is a smallest positive number, we can see there are no sign changes in the first column of the Routh array. So we can say the system is stable. Thank you.